In this video, I'm going to talk about the change of sign method and the bisection method to find the roots of an equation. In the earlier video, we've talked about we've used a graphical method to find the roots. And as I explained earlier, we are using this numerical method because it's difficult to actually locate the roots we cannot always factorize the equation. So we have to use these methods, whether change of sign, bisection, other numerical methods. First of all, let me say what do we mean by finding the roots? So you are not confused. Finding the roots, it's the value of x that makes f of x equal to 0. So we are looking for a value of x that result in an f of x or y equal to 0, i.e. the point of intersection. So where the curve cut the x-axis, that's y is equal to 0 here, same. So these values are the roots of an equation. These values here are the roots of an equation. Okay, so that's what we mean. And these values, if you plug it back in the function of x, it should give y equal to 0. Okay, that is the first point. The second point I want to mention in this video, some of these functions are so difficult to plot. It's so difficult. I'm going to show you some graphs, and then you can realize how difficult it is to actually plot it and to actually find the root of that equation. So these numerical methods make life easier, and I'll show you some examples what I mean by. And these are some examples, and you can see this function. This is 2 sine x minus x. So y, or f of x, equal to 2 sine x minus x. And you can see this equation has one root going through the origin, and the other root is here at 1.895, and that is another root here, minus 1.895. So this equation has 3 roots. In this one here, this equation, hyperbolic sine, the sine of x plus x minus x, we've dealt with this on the last video, and this has one root where the curve cuts the x-axis at 1.301. And here, this function, which is e to the minus x minus log x, it only has one root. The curve cuts the x-axis at 1.31, and here this function e to the minus x plus 1, this is this example we've done in the previous lecture, and it has only one root. And if you remember, we had to draw 2 graphs to find the approximate location of this root. And we're going to use this example again. I'm going to use this example again to use the bisection method, the interval bisection, and the change of sign method. If you remember from the last lecture, to find the roots to find this value here, we had to plot 2 graphs using the graph plotting method. And the way, I just remind you again, the way we've done it is we drew two graphs. One for the exponential function, which is something like that. It cuts at, this is 0 and 1, this point here, and we draw another graph which is straight line, which is x minus 1, and where they meet here we find that is the root. And this point here is this point here is minus 1, and this is all we know is between 1 and 2. Between the root would be between x equal to 1 and x in that range here, between x equal to 2 and x equal to 1. Now the change of sign method is going to look something like this. This is the same example number 1 in your notes, and it's what we do is we work out, well, it says here in the range 1 and 2. That means we try to work out the function of x when x equal to 1. So we basically put the value of x here, so basically e to the minus 1 plus 1, and that will give us this value here, and this is a plus 0.36 when x equal to 1, and this is positive, just not the sign here is positive. And when we try x equal to 2, the function of x will be equal to minus 0.86. What that means, in order for the y to change from positive, this is positive y, to negative, it has to cross the x-axis. So y below the x-axis is negative and above the x-axis is positive. So that means a presence of a root. And that is where the curve actually cuts the x-axis. And that only happens when there is a change of sign. So we've gone from a positive y to a negative. And that means the root lies somewhere in between. This is a very crude way to finding the roots. We cannot pinpoint the root exactly, but we know it's between x equal to 1 and x equal to 2. Well, we know from the previous slide, it's equal to 1.278, but this change of sign method doesn't tell us exactly where it is. A more accurate approximation is to use the interval bisection to get closer to that root, and as we will see in the next slide. So we know the root of the equation lies somewhere between x equal to 1 and x equal to 2. This condition is given by the example. So somewhere in between. So what we do, we use this equation here to find the function of x. So we say let function of x, which is the same as y, equal to e to the power minus x minus x plus 1. And then we find a function of 1 where x equal to 1, and this value will be a positive 0.36. And the same you do with the 2. You put the 2 in the equation here, in this equation, and you find f of 2, which is a minus 0.86. So the y values here on the x equal to 2, the y value is a negative here, and on the left here where x equal to 1, the function is, or the y value is equal to a positive value. So we know the root is somewhere in the middle. What we do now, we take a middle value. In this case is going to be 2 plus 1 divide by 2, and that's going to be 1.5. Remember, this is the value of x. So x equal to 1.5. And we do the same. We find f of 1.5. So we work it out, and we'll find out this is a negative value, negative 0.27. So it's a negative here. So we know what we're looking for. We are looking for the shortest distance between two opposite signs. So we've got the plus here, we got a plus sign here, a plus and a negative. So the root is not lying here, because this is negative and this is negative. So the root lies between the two different signs. So somewhere here in the middle. We'll take another value, and we'll take another value, let's say between 1.5 and 1. So that would be somewhere in the middle here, and that will be 2.5 divided by 2 is 1.25. This is x equal to 1.25. And we do the same. We work out 1.25 function of x equal to 1.25, and you will find this is equal to a positive value now of 0.036. Doesn't matter about the value, doesn't matter. It's the sign we are looking for, positive. So it's positive here. So really the root is not here. There's no root here, and is no root here in this area here. So the root lies somewhere here between x equal to 1.25 and x equal to 1.5. We do the same process again. We take the middle value between 1.5 and 1.25, and that's why it says interval bisection. So it's going to be somewhere down here, and it's going to be an x of 1.375. 1.375. We do the same, f of 1.375, and you'll find this is equal to a minus 1.2. Minus 1.2. So that is a negative value. So here is a negative value. Now we know this area doesn't have a root. So the root lies between the positive and the negative. And let's take another midpoint value, and this time is 1.25 plus 1.375. The mid value here is 1.31, and we do the same again. The function this time of 1.3125 is going to give us a minus 0.043. So the root lies between this point here, this point here, and this point here. So this is 1.31. So x equal to 1.31, and this is accurate enough for two significant figures. So we say x equal to 1.3, because the one before that was 1.375 and this is 1.3, so that is close enough to the requirement of the answer, which is two significant figure. Okay, so x is equal to, or the root is at x equal to 1.3, and that is accurate to two significant figure. And that is the answer using the bisection method, and which is close enough to the actual the value of 1278. Okay, so just to summarize, the curve of this equation here will cross the x-axis. It will cross the x-axis at a point close to x equal to 1.3, and that's what we mean by the root. So it's not crossing in this area here. The curve is not crossing the x-axis, and it won't cross it in this area here between 2 and 1.375. So it's crossing somewhere down here, and that will give us the root, the root and the only root of this equation, a value of x equal to 1.3, and that is accurate to two significant figures. Okay.